Hello, everybody. It's a pleasure to meet you, speaking into the void here. I'd love to have been there, but here I am, all alone in Oxbotica. I'm hoping I can remember how to set the alarms as I leave. So it's a real pleasure to talk to you, and I'm going to talk today about scaling data and data scaling as sort of a palindromic problem that we're in. And the work I'm presenting here is done by the Oxbotica perceptionists. You know who you are. Big shout outs up. So thank you very, very much. So just, why is that not working? Right, just a little bit here about Oxbotica. So Oxbotica is a software company. We're not trying to build a fleet of vehicles. We're trying to build what we call universal autonomy. And our key thing is the common code for all domains. So what you're seeing here is exactly the same stack running in 4 domains. On the bottom left is a mine, and then we've got around London, we've got off-roading, and then we've got some delivery vehicles that we ran around West London a couple of years ago. So that's what we do. And today's talk is going to be about a subcomponent of this. This won't be a surprising slide, but there are these 4 pillars, if you like, of autonomy. Where am I? What surrounds me? What happens next? And what do I do? And not surprisingly, I think a good engineering approach is to try and attack all those problems with both optimization and ML. So that would be like a 19-hour long talk, which I wasn't allowed to do. So today, I'm just going to talk about what surrounds me using the machine learning outlook for doing that. And I'm going to take that mostly for the on-road domain using vision and LiDAR. I won't be talking about using radar to do that, or we have that coming. And I won't be talking about doing this off-road in mind. It'll be mostly the on-road business today to give you some sort of scope of where we're going. All right, okay. So here's the beast that we need to feed. Hopefully that's streaming for you. It seems to have paused a little bit there. Yeah, it seems to be a bit jerky. So this is what we want to be able to feed, is a perception system on the right hand side using a camera. Here we're doing real time 20 hertz, 5 cameras, instance segmentation, depth completion on very, very low power. This thing runs on a single HD camera on a 30-watt processor. On the left hand side, they're the same thing happening in laser light. So I do hope these videos stream a bit better than they are at the moment. So that's what we want to feed. We want to feed that beast, and that guy needs some data to be trained up. So this talk is going to be about how we built the system to produce this curve. So this is something we care a lot about. So we want to be in the green belt there because that's super and it's fast enough to run real time. If you're in the red, it's not competitive enough for us to be able to run real time. So we want to do really well running real time on HD cameras on low energy and be fast. And it's quite interesting, isn't it? Sort of a log frontier here of where these different systems live. So the yellow is not so competitive, and the new territory line is where that blue arrow points. So what I'm talking about today is about staying in that locus of success, and we want to move up that MIOU axis to give you some sense for what we're doing. Okay, so look, how are you going to get these data sources? So perhaps one of the obvious things to move for, would be simulation. So here's one of our simulations running. It's the same code running in a mine, or if we're running in a city. And this is really good for scenario simulation. It's not great from these pictures for producing data for machine vision, but in terms of tricky scenarios and that nightmare case where the 7 vehicles are doing something crazy you never thought of and doing perturbations around that, it's a nice thing to have as a simulator, and it's important to us. Now, some sensors are quite easy to simulate. For example, here, this is that same simulator doing some ray tracing and producing simulated returns. And of course, it's colored here by semantics. So, we can pick out when we've got vehicles that are being seen at different distances, and we can simulate the physics, and we can simulate noise models. And this can generate something like 60,000 frames in an hour or so for training up the ML in laser space. So that's a fairly easy way to to do it. It's very cheap. Once you built the simulator, it's massively parallelizable. We can run this in the cloud. The visualization and the header are entirely different. So, and we've got a great games team that have built this for us. So yeah, that's one thread that you may do. I don't know what this music is. That was not supposed to happen. 1 second. Gone the wrong direction. Yeah, that's what happens if you play without the music. So forgive the music, that's not supposed to happen, but these are the kind of places that we drive in. Oh dear, oh dear. 1 second. 1 second, I'm just going to drop out and stop that horrendous music. Hang on, give me a second. That probably felt like a really good idea at some point, but okay, let's go. Oh. Okay, right. I'm going to do it this way. So to give you some sort of the sense of the places that we're driving in, you know, it's a typical urban scene that we're driving through here. This is a sort of a local town called Kidlington. It's great because statistically it's really average in terms of citizens, age groups, traffic use. So the normal show. And down here, of course, is where we work in off-road. So same vision system here running off-road. That's in a mine at night, down through a forest. And this is all closed loop using a pure vision system. So the good thing about using a vision system that good is we're getting sort of precision of the order of a couple of centimeters in terms of X and Y, and 0.1 degrees roll, pitch, and yaw. So it's extremely, extremely precise. So we know where we are the whole time really well by using cameras. And so one of the things you could then do, of course, to produce some training data is Dream. So you can drive and you run a weak classifier and a weak localizer in terms of semantic localizer. And then you can optimize over a few minutes, and then you can install into your map. You can discover where your things of interest are semantics. So here we're doing traffic lights. At the top right here, this is just going through a data set. And at the bottom right are the optimized locations of those traffic lights by running a bundle adjustment overnight. So that's kind of cute. So that's a way in which we can now discover without human labeling where elements that we wish to get training data from are in the world. But because we've got the localization so good, as we're driving, even at great ranges, we can now start to spot the traffic light. So there at the bottom left there where it goes green, I'm seeing that traffic light. I know where to look for that traffic light because the localization is so good in terms of roll, pitch, and yaw. Those are the ones that really matters. And at the top there, you can start to see the images of the traffic light coming into view on a very, very average camera. So what have we done there? We've used our localization to install something into a map, discover where that is. And then as we're driving through, we can then gather more and more data because we know where we are. So we then have a sort of a soft labeler for us. And so that's quite a nice self-labeling source for localization. And again, no humans have to touch anything there. So that's quite a nice cheat. Now, of course, maps are free. It costs nothing to build a HD map. So this is one of our maps on one of our test sites here. Just we're visualizing that. Of course, it can be colored in with laser. And again, this is all being driven just off the vision system. We're not using any RTK or any INS here. This is just open loop mapping. So those are free. So what can we do with that sort of tool? Well, one of the things that we could do is in laser light, we could quickly sketch out the boundaries of a road that might be of interest, or we can actually automatically discover that. And because we can then cross-localize what we see in laser light into the images, and experience after experience, day after day, we know where we are, we can then copy labels across into different scenes. So here we're copying the labels that came from laser into the sun scene, to the cloud scene, and to heavy rain. And you know, we haven't had to do any of that labeling. So here, for example, we're looking for road markings and generating data for road markings. So that's working quite nicely for us. And we're getting a more than a 10% jump in terms of recall in doing that. So again, it's one of the tricks that we're using is because we can build our maps, because we can localize, and we can do that so precisely in 6DOF, we can generate and we can, if you like, expand and multiply training data for ourselves. So that's quite a nice trick for us that we do like to look into. Okay. The next thing that we can do is to use both vision and geometry. So because we have those HD maps that we're driving through, and because we've got the localization, we know where we're going to be in the future if we're playing sort of time backwards. We can then project the depth, the actual depth of something back into an image, and then we can start to do some depth completion work there. So here we're using laser as a teacher for depth completion in images. There's some trickery you have to do about removing dynamic objects, but that can be done from multiple viewpoints with some geometric tricks there as well. So this is very satisfying, and this works really, really nicely. So what you're seeing at the top there is the images coming in, and then there's a sparse laser which is being completed for depth, and that's being used to train depth completion in the images and depth map estimation in the middle row coming through there. So one of the other tricks that we can use. Okay, and of course, and here it is actually using a sparser sensor, so very, very sparse range sensor, nothing like a Velodyne here, a very different kind of sensor for depth completion at very, very low costs. So that's working quite nicely again for us. So that's an unsupervised way in which we can generate training data for us at scale. Okay, right. So, another thing that we've been looking at doing is generating road synthesis for these lines as well. So one of the things that we can then do, because we've got these trainers, is produce AIs that are going through and they're finding where the road markings are, and they're doing it in a semi-parametric way. And so I know the boundaries and the class of the boundaries, and then we're synthesizing data of the different class types here. So for example, if you've done this left-hand column here, I may have blue boundaries and I'm keeping the blue boundaries constant, but green and red mean something different semantically, whether you can pass or it's a passing lane, and we synthesize those. So those scenes never existed at all. And I'm going to be talking about some of the work we do for data synthesis in the coming minutes and closing minutes of this talk. So again, this is another approach where we're using the some classical methods to find out where we are in the road for a view, find some initial road boundary markers, and then do data synthesis to generate new road markings for doing that. And that's a very data efficient way to do this. So, okay, so just nipping back to our simulator, we said that photorealism is a bit tricky, but so the simulator is great for physics and it's great for scenarios and it's great for laser, but what's it like for actually generating scenes photorealistically? Well, it's great, but it's just a bit wrong. So, but what it can do is produce semantic maps like the one on the right, where the kind of object is colored. So that's just a semantic mask. Wouldn't it be really cool if we could take that kind of scene and then we could paint it? And so we could turn that into photorealism, which of course is something that we can do. And people have got a problem with, deep fakes. I think I'm a huge fan of deep fakes. I think it's a great thing. It's not fake news. It's really great. And so these are two scenes here that never existed. So we had this starting with the semantic image on the left, and then we've trained to in-paint the pixels correctly, and even down to the traffic lights and the road signs. It's not perfect, right? I mean, if you look at some of the cars, they're a bit skew-iffy on the right-hand side. It's not perfect, but in terms of data augmentation, this is quite a rich data source. So, and of course, having done that, if we have parametric knowledge of some of the articles on the road, like arrows and road markings and center lanes, we can parametrically switch these things around to scenes that we've never seen. So again, the pictures here have never really existed. We start with semantics, we learn to in-paint, and we're flipping the arrows around in ways that would never really exist, but that doesn't really matter. We don't want to just train on the very simple road markings. We might want to train on Baroque road markings as well. So here's another couple of examples of in-painting here. You see the buildings aren't quite right, but the roads in particular, we put a big cost term on getting those roads right here. So how do we do this? Well, we start with a small amount of label data that come from our simulator, or maybe it's a few hand label semantic maps. And we've got some images that perhaps have been transformed, and I'll come to that in a moment. Perhaps we put some rain on the lenses, and then we've got some original images as well. And so a small labeled set, and then we've got an unlabeled set of the other conditions that we want to simulate, and be that rain or snow or nighttime. And then what we're going to do is, I think, probably what you would expect we would reach for is use a CycleGAN then to synthesize and change the appearance of these images into these different conditions. So our original images will now be transformed to images that have the appearance transfer of being wet, snow, or night, or whatever we choose. And so, for example, here's daytime to nighttime. These are always nice when they come out. I love the way it sort of like fantasizes where the light should be. And there was a particular tree in Oxford that always seems to catch on fire, because it always wants to have orange lights in the middle of it. But really, it does look quite compelling. And so this is a straightforward style transfer. These things aren't necessarily easy to train, but with a bag of tricks that we've developed, that's it's coming along really quite nicely. Okay, and again, you know, we can change the weather conditions too. So here you go. Here we have with a CycleGAN, it's painting in snow. We never actually saw that snowy image on the right hand side. So these are the sort of the adherent conditions that we might stick on top of the images as well. And in terms of how do you train for rain, well, actually, quite a nice trick there is actually we squirted water onto one of the lenses and just drove around for a while. We actually also built, and this brings back to that point about the Newton's diaries, you know, where raindrops are is actually Newtonian. So there is actual physics you can run to build a simulator that simulates rain. And of course, we've got both images are identical, but one's got rain superimposed. And so the right-hand side there, one of those images is fake. So the original image is at the top, and then one of them actually has rain and one is synthesized rain. And I think the synthesized one doesn't have the streaks running down it, but it does have those raindrops on it. So again, so we can synthesize weather conditions that we've not seen before. Okay, so with our transformed images from our CycleGAN and adding our semantic map, we can take that through a typical SPADE system to produce a fully synthesized image, and we can do it under any condition because we can do our style transfer. So that's working really quite nicely. And then, of course, what we can do is we can decide which parts of the scene that we want to mess around with. So we may decide that we actually don't want to transform everything. We might say, well, actually, I'd like to transform the sky conditions to be cloudy, or I'd like the lighting conditions to be different, or I'd like to mess around with vehicles, but I don't want to mess around with people. So because we've got the semantic map, we kind of like have a way to modulate what we're going to be synthesizing. So in the end, we can come up with a final synthesized image, which is really quite nice. So again, these images never existed. Quickly, the pylons aren't quite right when you look at them, but on first glance, they're not bad, and they're ever getting better. And again, the synthesis there of that motorway scene, that's a very simple thing to simulate. And again, here, some other ones. Again, they've just done quite a good job on the trees, but I think it's particularly fond of the autumn or the fall. And here we are messing around by synthesizing some people, and that building's okay. But again, it's enough to augment that this for a semantic segmentation probably should be building for data augmentation purposes. Again, another example there. Okay, and then of course, what we can do is sort of class swap. So, oops, yeah, this is going to work. This is going to be, it's quite hard to spot the difference, but on these cycling images here, we're going through and we're switching out buildings and swapping them for trees and other similar classes. So quite often if you watch, I'll keep it cycling. Every time there was a tree or alongside a tree, we replace it with a building and vice versa, or different kinds of trees. So so we've decided here that actually we're thinking the trees are confusing us, for example, around the traffic lights, and so we want to synthesizing those in a different way. So that's, you know, bringing this all together, it's quite a powerful arsenal. And I guess my message is there isn't one, you know, even I'm from the land of Tolkien, there isn't one way, I think, to rule them all. I think that if you are building a system for an AV, you should leverage every trick that you can. If you know where you are and you have a localization and mapping ability, then you should use that. Of course, we should train AIs to train AIs. This is a form of curriculum generation. Of course, we should do that. I think that's a very powerful idea. And of course, it scales beautifully. So, we can go to a particular environment, we can get some training data from that environment, and we can say, what would this place in southern Germany look like in rain or in snow or in different lighting conditions, and get some sense of how we're actually going to perform by almost like, if you like, instance installation in those places. So to finish though, some sensors really do remain hard. I think we're synthesizing radar data. I think that does remain hard. This is us passing through a car park here very, very slowly, and segmenting out where those vehicles are using a particular kind of FMCW radar. I think those sensors do remain hard, but they are fully next. So I put this slide together just at the end. I don't think I've ever finished a talk on time, but it's because I'm not getting interrupted or picking up on audience interaction. So forgive me. But there's, bringing this all together, what do I think? I think the experience method of going out lots and lots of times, but then being able to transfer labels across from different scenes, from different times you go out, because you have that localization. So you can project elements, if you like, of a 3D structure into your image and use that as a label. I think that's very powerful. Obviously, you can simulate some sensor data. You can do synthesis of rain and adherent properties. That's obviously important. And you can do whole image synthesis as well. And of course, on top of that, you would have your normal simulation. So we're really strong advocates here at Oxbotica of reaching for everything that you can possibly think of to get you that data in a way that is sublinear. I mean, ideally, we want logarithmic scaling. Now, going out on the experience day after day and transferring labels, that's linear. Okay, so that's the worst we could possibly do. But the new stuff on the data synthesis, I think that's really a whole new vista for what we can generate. And we're seeing really spectacular changes in our perception system because of that. So, I mean, on that, I'm gonna close. I'll give you a bit of time to catch up. I want to say thank you for taking the time to listen to me in your living rooms or wherever you are. I'm really sorry I can't be there, and maybe next time we'll be able to get together. And a huge call out with a thank you to the Oxbotica perception team. And I don't know if I take questions now, but I wanted to thank you for your time. Thank you very much.